Great, thanks. Um, Good evening, everyone. A warm welcome to all of you joining us today for this exciting guest talk organized by the Astronomical Society of University of Peradeniya. And we are thrilled to have you here with us to explore the intriguing topic, Devouring Dwarf Galaxies with Galacticus. So before we begin, just a quick reminder. If you have any questions during the session, please drop them in the chat box so it is easy for us to efficiently address the questions during the Q&A session. Now, to formally kick off our session, I would like to invite the President of the Astronomical Society, Ms. Chamatka Samaraheva, to introduce our distinguished guest speaker.
Good evening, everyone. Welcome to another insightful session in our guest lecture series. It's my pleasure to introduce our guest speaker for today's talk, Dr. Sachi Weerasooriya. Dr. Sachi Weerasooriya works as a postdoctoral researcher at Carnegie Observatories. Her work focuses on modeling galaxies for upcoming large-scale astronomical surveys such as Rome. A key part of her research involves the accurate modeling of emission lines and the calibration of galaxy formation models using the semi-analytic model Galacticus. Her previous research has provided valuable insights into the dwarf satellite galaxies of the Milky Way and Centaurus A. She is also interested in the impact of major galactic images on the stellar streams, exploring how such cosmic interaction shape the structure and evolution of galaxies. Beyond her scientific work, she brings a unique creative dimension to the field. She is passionate about connecting science with art through scientific illustration. Thank you, Dr. Sachi, for accepting our invitation and joining with us today. We are excited to hear from you. So over to you, Dr. Sachi. Thank you.
Thank you so much, Shamatka, and everyone here for giving me the opportunity. Um, okay. Mhm. Hello, everyone. My name is Sachi Weerasooriya. I'm a postdoc at Carnegie Observatories in Pasadena, California. So today I will talk to you about Devouring Dwarf Galaxies with Galacticus. This is work that I did during my PhD with my collaborators, Mia Soder-Boville, Andrew Benson, Matthew Taylor, Massimo Ricordi, Alexi Music, and Cameron Leahy. So before we get started, let's go to the beginning of everything, the Big Bang. The universe was a hot fluid just after the Big Bang. And after a fraction of a second, it started expanding during the period which we call inflation. The quantum fluctuations that froze out during inflation grew over time until they become gravitationally unstable and form the dark matter clumps. Dark matter clumps or dark matter halos are the basic structures holding everything in these galaxies. These, baryonic matter, such as gas and stars, follows gravity. So, the baryonic gas followed gravity and condensed into the gravitational potential wells of these dark matter halos. This eventually formed the first stars in the universe. This is at around a redshift of 11.4. Light from these first stars reionized the hydrogen in the universe. So, the epoch of reionization, as we call it, lasted from about a redshift of 15 to a redshift of 6. So, this is the period that we are talking here. This was followed by the formation of the smallest galaxies in the universe. The smallest structures, galaxies, are known as dwarf galaxies. And these are fundamental to the structure formation of the universe because they are the building blocks of larger scale galaxies. Now, today I'll talk to you about dwarf galaxies. Now, over the next 12.5 billion years, the smallest galaxies merged in to form larger galaxies. This process is called hierarchical structure formation. And the larger galaxies formed clusters of galaxies. And today we are at a redshift of 0. We can see many, many galaxies in our universe. And we can observe this hierarchical structure formation in cosmological simulations. Now, as human beings, we don't live that long, right? So we can't see how the universe evolves. So simulations are a great tool to visualize this process and understand the physics of what's going on in galaxies. So if you look at the filament-like structures that you see in this picture, the blue filaments are observations from Sloan Digital Sky Survey. And the red filaments structures that you see here, the cosmic web, are from simulations. So you can clearly see that the predictions of the large-scale cosmic filaments from simulations agree with observations. So simulations nowadays can predict this large-scale structure of the universe when they are based on cold dark matter theory or lambda CTN. What about the smaller structures? Now we are able to reproduce the large scale structures, but we need to understand about the smaller scale structures of the universe as well. Now these are dwarf galaxies. What are dwarf galaxies? Dwarf galaxies are fainter than about minus 18 magnitudes and at a redshift of 0. Now this is this is usually less than 10 to the 7 solar luminosities. So 10 to the 7 the brightness of the sun. And we can see many classical dwarf galaxies around our galaxy, Milky Way. And this brightness or the absolute V-band magnitude scales as minus 2.5 log of the luminosity of a certain galaxy. Now I'm highlighting two galaxies right here, the Large Magellanic Cloud and Pictoris 1. LMC, or the Large Magellanic Cloud, is one of the largest satellite galaxies of the Milky Way, or the largest dwarf galaxy in the Milky Way. And Pictoris 1 is an ultra-faint dwarf galaxy. These are not visible to the naked eye. But LMC, you would be able to spot this galaxy if you go out and look at the night sky. So now let us look at a closer look at the Large Magellanic Cloud. And we are zooming into a Large Magellanic Cloud, or the LMC. This satellite galaxy is 10 times less massive than the Milky Way. In dark matter halo mass, this is 110 solar. So now let's zoom back out and look where we are. We are right here in the local galactic group. And this extends up to about 15 to 19 megaparsec. Here, 1 parsec is equal to 3.2 light years. And if we zoom in closer, we are in the local group. Local group consists of the Milky Way and the Andromeda galaxies. Both of these systems are similar in mass and surrounded by these tiniest dwarf galaxies. These are called satellite galaxies. They are falling in as time moves forward. These satellite galaxies fall in to the gravity of these larger galaxies. Now, several years ago, we only had discovered about 10 dwarf galaxies due to limitations in surveys. The photographic surveys discovered about 10 classical dwarf galaxies. So here you can see Draco, Leo 1, Carina, SMC, Sculptor, Fornax, LMC. These are classical dwarf galaxies. And these are also some of the brightest of the dwarf galaxies, brightest of the faintest. And towards later, we got digital sky surveys like Sloan Digital Sky Survey, Dark Energy Survey, which discovered hundreds of galaxies. So now we have many more observations to look at to understand the physics of dwarf galaxies in our own backyard or in our own Milky Way. So this is amazing. Milky Way is a great place for us to understand the dwarf galaxy physics because of this. Completeness of observations allows us to test our models in this system. So the Milky Way, both Milky Way and Andromeda, has a mass around 10 to the 12 solar masses and surveyed by Sloan Digital Sky Survey, Dark Energy Survey, and PANDAS surveys. Milky Way has these dwarf galaxies I'm highlighting here. And on the larger end of the spectrum, we have larger mass clusters like Fornax and Virgo clusters. Now, these two clusters are around 10 to the 14 to 10 to the 15 solar masses. And they also host dwarf galaxies. Somewhere in the middle, there's a galaxy called Centaurus A that's around the 10 times more massive than the Milky Way, or 10 to the 13 solar masses. This galaxy is a large elliptical galaxy surveyed by Pisces and SCAB surveys. So, what I'm trying to tell you here is that dwarf galaxies live in different kinds of mass environments. And it is important to understand how these environments affect these dwarf galaxies. Why? Because dwarf galaxies are the faintest and they're the most sensitive to their environments. They have very shallow gravitational potential belts, which can expel any gas or stars in them. So it's very crucial to understand how environment affects these galaxies in different types of environments. So now we saw observational data from these different surveys and what we have. Let's now look at the scope of simulations that we have today, as of today. Now, this is a figure from Nelson et al. 2019. This shows the baryonic mass resolution on y-axis, shown in solar masses. And on the x-axis, you can see the number of galaxies that resolves more than 10 to the 9 stellar masses. In essence, the y-axis shows the resolution. So from top left bottom to the top, the resolution of the simulation increases. So you can look at the faintest of dwarf galaxies as you go from top to bottom. Sorry, bottom to top. From left to right, the number of galaxies increases in these simulations. So the blue box I've shown you here resolves the faintest dwarf galaxies. But this comes at a price. These are highest zoom-in cosmological hydrodynamic simulations. That means these simulations resolve the faintest galaxies, and also they have all the physics of stars, gas, and dark matter in them. This takes months of runtime or even years to run, so it's very expensive. As a result, we have to sacrifice simulating larger number of galaxies. On the other hand, we have larger cosmological volume simulations like TNG 100, TNG 50 that allows us to simulate larger number of galaxies. But because they are so expensive to run, we have to limit the resolution of these simulations. So we cannot resolve the faintest dwarf galaxies. We can maybe look down to about small magellanic cloud and the large magellanic cloud, which are the largest of dwarf galaxies. We are not here up here yet, where the next generation high resolution cosmological volumes. But why do we need them? These simulations are limited by either resolution or statistics, but we need the next generation high resolution cosmological volumes. The reason why is this. We are entering into this new era in astronomy with Nancy Grace Roman Space Telescope. Roman has a field of view that's 100 times more powerful than Hubble, and it's going to bombard us with unprecedented amount of observations. To give you an idea of this, let's look at this galaxy. Hubble would take about 432 pointings to cover the area of this galaxy. But Roman would need only 2 pointings. So this is the power of Roman Space Telescope. It's going to overwhelm us with many observations. So at simulators, we need to be ready to tackle these data sets and target what we want to look at. So our models need to be ready in order to deal with to supply the demand of observations. So the question is, are our models ready? As I showed you earlier, not quite. Because our hydrodynamic simulations in the field are not ready to tackle this yet. But don't worry, because we do have something. This is where semi-analytic models comes to our rescue. Semi-analytic models uses a simpler framework to solve galaxy physics using analytic approximations. It will solve differential equations for different physics of dwarf galaxies or any galaxy, for inflow of gas, gas cooling, star formation, stellar feedback and outflows, and many more. And it builds onto a merger history of dark matter halos. So you need to have an embodied simulation or build dark matter halo merger history and how galaxies evolve in this type of models. The biggest advantage is we can adjust the astrophysical prescriptions and parameters pertaining to each of these processes in this shown in this baryon cycle I'm showing in this figure. And all of this comes at a very low computational cost. You can run a model in your own laptop in about 20 minutes. And this is 1 million times faster than hydrodynamic simulation that could take months or even years to run. So the model that we are using is called the Galacticus by Benson 2012. And of course, it's based on a Marvel villain, so please don't sue us. Now, this brings us to the question, can we use these semi-analytic models to reproduce the classical dwarf galaxies? These models are making approximations to solve these differential equations. So, can we still reproduce the observations that we see? The answer is yes, and I'll show you how we do this. So, now I'm going to show you an n-body simulation. This is not a simulation that I ran, but something similar. So here you can see an n-body simulation of a Milky Way-like galaxy, or as we call it, a Milky Way analog. A Milky Way-like simulation that has the same mass as the Milky Way and environment. So there are satellite galaxies that merge in to form larger galaxies in this simulation and forms this satellite system of the Milky Way in this simulation. So this n-body simulation contains information on the properties of dark matter halos, their velocities, masses, their sizes, and many other things. But this simulation does not have any gas or stars or any star formation physics. So we can use one of these n-body simulations to process this simulation and apply the baryonic physics or the star formation physics using the semi-analytic model. And what we do is we then use different compare our models to observations to calibrate and tune this model to get a good fit. Okay, so how do we calibrate our dwarf galaxy? We calibrate this with the Milky Way dwarf galaxies because the observations are very much complete and this is a well-known system. So we start with what we know. Here you can see the luminosity function. This is the cumulative number of dwarf galaxies that we see at absolute V band magnitude. Absolute V band magnitude is a measure of brightness. So as you go from left to right on x-axis, the brightness increases. And the faintest dwarf galaxy, there are many more faintest dwarf galaxies than the brightest, as you can see from this figure. And we use observations from Carnegie 2012 to compare and tune our models. We also compare our model to other hydrodynamic simulations like mean justice league. These simulations are very high resolution and simulates Milky Way analogs. And also to Fire 2 simulations, these are data from Ship et al. 2022 of different mass Milky Way simulations. And our model is shown in pink right here, and you can see we are able to tune the physics to match the observations. And here we are tuning different parameters and physics pertaining to mass accretion, gas cooling, and outflows. So some things that we tune are reionization physics, cooling physics, ramp pressure stripping, tidal stripping, efficiency of tidal stripping or due to tidal fields, and so on. Simultaneously, we also calibrate the luminosity metasity relation. Now, why is this plot important to dwarf galaxies? I told you previously that dwarf galaxies are very sensitive. They have very shallow gravitational potential wells, so they can expel any stars or gas in them. And metal abundance is an indicator of this stellar feedback. So that is why we are looking at this plot. So it's very crucial to get this relation right. So on the y-axis, you can see the ion abundance with respect to hydrogen and the absolute V band magnitude on the x-axis. And as you go from left to right, the brightness increase. And I'm showing the observations in green and our models in pink. What we do here is vary the physics, the parameters that goes into this differential equation right here. The velocities and exponents of this determine the stellar feedback physics of our model. Now, all of this happens all at once together. So it's not just one equation that's at play here. So you can see we are able to reproduce the dwarf galaxies down to the faintest of dwarf galaxies. This was amazing and something that we did not expect in the beginning. Now, this is at a redshift of 0 or the present day. Without any further tuning to our model, we are able to reproduce other properties as well. So here you can see the velocity dispersion of these dwarf galaxies shown on the y-axis at the absolute V band magnitude on the x-axis. Similar to previous plots, I'm showing the observations in green and models in pink. And we are able to reproduce these observations very well. Even the mass to light ratios, the ratio of dark matter halo mass to light produced in our models agree with observations, which is amazing because we are not tuning our model to these two relations. Now, this is only at the present day. What about in the past? What about the star formation histories? Now, this is a plot from Weiss et al. 2019. And it shows the time taken to gain 90% of the stellar mass versus the time taken to gain 50% of the stellar mass, tau 50, on the present day. Now, before I explain this plot, let me step back a little and tell you what this tells us. Star formation history tells us how the stellar mass evolves with time. On the x-axis, you have look back time. So we are looking back in time to the Big Bang. And the stellar mass is the mass of stars in these galaxies. So tau 50 is the time taken to gain 50% of the stellar mass that we see at the present day. And tau 90 is the time taken to gain 90% of the stellar mass that you see at the present day. So these are good indicators of star formation history of a galaxy. Now, if you go back to this plot shows the tau 90 versus tau 50 for these dwarf galaxies. And each point is colored by the brightness and sized by half light radius. Now, what does our model look like? Our model produces something like this. So you can see we are able to reproduce the relation in tau 90 versus tau 50 with Galacticus semianalytic model. So we not only reproduce the ultrafaints with the semianalytic model for multiple relations at a redshift of 0, but we are also able to reproduce the star formation history simultaneously. Now we have calibrated our model to a well known system, the Milky Way satellites. Now, this poses us the question, does star formation physics of dwarfs depend on environment? What if we look at dwarf galaxies in a different system, like Centaurus A, that's 10 times more massive? So we expand this to a new environment, Centaurus A. Centaurus A is the closest elliptical galaxy to us. It's 3.8 megaparsec away. Again, parsec is equal to 3.2 light years. It's the most accessible to us in terms of observations, and the mass of this galaxy is poorly constrained. And most excitingly, we will have new observations in the near future with Nancy Grace Roman Space Telescope. Now, this galaxy is surveyed by two surveys, HISIS and SCAPS. Both look for dwarf galaxies and the smallest galaxies in the universe, and extends up to about 150 kiloparsec from the center of this galaxy. However, something that we should keep in mind is that compared to the Milky Way, Centaurus A is limited on the star formation histories or even velocity dispersions. So the second question that we are going to ask is, can star formation physics of the Milky Way satellites reproduce Sene dwarf galaxies? Because we don't know much about dwarf galaxies of Centaurus A, we are going to apply the same physics that we found for Milky Way dwarf galaxies to a Centaurus A like simulation that has dwarf galaxies with dark matter halos. Now you can see here, we are asking the question, does the same recipe work for Sene satellites? Here we have run several models, N-body simulations, and EPS merger trees, which is another type of model for different mass Centaurus A simulations. And the models are shown in green and blue, and the observations in purple. Again, this is showing the cumulative number of dwarf galaxies per absolute V band magnitude. And as you go from left to right, the brightness increase. And we are able to reproduce the overall shape of the luminosity function for the Centaurus A satellites within 700 kiloparsec, which is great because this possibly means that the same star formation physics of dwarf galaxies applies to Centaurus A satellites. If we go in a little bit closer to about 150 kiloparsecs from Centaurus A, our models are again shown in green and observations in purple. And we are able to reproduce this luminosity function within the inner region of Centaurus A as well. Now we are looking at the inner region because it's more complete in terms of observations. We also looked at the luminosity metallicity relation. This is very important to capture the stellar feedback of dwarf galaxies because they are very sensitive to their environment. So here I'm again showing the observational data of iron abundances in purple and our models in green. And the models suggest that the iron abundance of these galaxies are very similar to that of the Milky Way satellites. So even if these galaxies live in a galaxy that's 10 times more massive, they seem to be unaffected. Why? We don't know exactly why this is the case. Now, next, what we have here in this plot is the half-light radius, the radius at which half of the light is contained in a galaxy. And I'm plotting the half-light radius in parsecs versus the absolute V band magnitude, the brightness. And you can see the observations in purple and models in green. And we are able to reproduce the sizes of these galaxies well. We also looked at velocity dispersions of these galaxies. Velocity dispersion probes the depth of the potential well, so it tells us about the dark matter halos of these galaxies. And you can see the Milky Way satellite observations in the triangles in gray, and one observation that I could find of Centaurus A in purple, and the models in green. So the one observation, the model agrees with just one observation. Of course, that's not enough to say about this satellite system or the observations, but we can say that they look very similar to the Milky Way satellite, at least in our prediction. So these predictions, um, like star formation histories that I'm showing you right here, shows the fraction of stellar mass formed at redshift of 0 or today. Each star formation history here is colored by the luminosity, log of luminosity, and divided into subcategories based on their brightness. So the faintest are on top left and the brightest are on bottom right corner. And there are two observations that I'm showing you here, which have very high error bars. So as I said before, the star formation histories of Centaurus A hasn't been explored much, and we need observations in the future. So these are basically predictions that will be testable in the near future with Roman Space Telescope and Vera C. Rubin Observatory. So summing up, we looked at two questions. Here we tried to answer, can we use semialtic models to reproduce classical dwarf galaxies? The answer is yes, we can reproduce the properties of Milky Way dwarf galaxies and their star formation histories simultaneously, down to the faintest SDSS ultrafaints. And we can use this star formation physics to understand whether dwarf galaxy physics depend on environment. By applying this Milky Way dwarf galaxy physics to a Centaurus A like simulation with dwarf galaxies. And what we found is that Milky Way dwarf galaxy physics reproduce the overall dwarf galaxy population in Centaurus A. And our predictions are testable in the near future with Roman Space Telescope and Vera C. Rubin observatories, which is exciting. And to overall, what I want you to take away from this talk is that dwarf galaxies are fundamental structures that are the building blocks of larger galaxies. And these are crucial to understanding how galaxies evolve in time. And also, um, in a time where we are living in a time where there's going to be telescopes that's going to give us many more observations, bombard us with numerous observations in the future. So we need to have models that has the resolution and statistics that can predict and target these observations. And semiotic models that I'm showing you right here is the answer to get the resolution and the statistics that we need for upcoming surveys. And with that, thank you so much for giving me this opportunity. Uh, yes. And answer any questions if you have any.
Thank you so much, Dr. Sachi Weerasooriya, for that fascinating and very insightful session. It's truly inspiring to get a glimpse into the cosmic events that shape our universe. So now it's time for the audience to raise their questions and get anything they want to get clarified.
Actually, may I know what is the programming language you are using for your simulations?
Yeah, absolutely. So Galacticus was written by Andrew Benson, and it's written in Fortran, C++, Python, Perl, like a few different languages, but mainly Fortran.
Okay, thank
And something that I should say is Galacticus is an open source code, so even you guys can like use that to download the Galacticus semantic model and use this for your own research.
There's one more question, Dr. Sachi. Like, do we have a number wise, like, for the accuracy for the model using Galacticus before we get the observations from the Roman spaceship, like number wise accuracy?
Right now, I don't have any numbers, but like you can definitely make predictions targeting this survey. Um, I don't have a number to give you right now, though.
Yeah, thank you.
you. Actually, madam, it would be insightful if you can describe your academic path.
Yeah, absolutely. So I pursued a bachelor's in physics and mathematics, and then I would say it's very useful if you can get research experience as an undergrad and publish few papers if possible. Um, and like reach out to you can also like um yeah so like in doing undergraduate research work is very important to get into a graduate school. So so I had some of that experience, and then in graduate school, um something that's not talked about much is um picking a good project that you enjoy doing, and also picking the PhD advisor. So you have to talk to like the potential advisors and see how like what their plan is for the next few years, because a PhD would take a minimum of 5 years or more, 5, 6, or even 7 years, depending on where you go. In the US, the minimum is 5 years, usually takes more than five. Um, and it's very important to like talk with your advisor about the projects and see if you, as a person, and if you can work with your advisor. So that will definitely help. Um, having like yeah, so like getting involved in research and like other activities would help also to like highlight your application among other applicants. Yeah. Did I answer your question?
Yes, madam. Thank you.
Yeah, I'm happy to like give any uh, advice, or like if you need any help anytime, feel free to email me.
So if there's any more question, you can ask from Dr. Sachina. Dr. Sachi, there's a question in the chat box. Let me read it out for you. How handy is machine learning when it comes to building simulations?
So it's very important. In terms of building simulations, machine learning can be used to make emulations like type models. I think there are some like students that I know, graduate students who work on this with Galacticus. I don't personally work on machine learning, but it's very useful to even like I told you like semiotic models are faster, but with machine learning you can make it even more faster if you can use machine learning algorithms to learn from the results and make emulations. So that way it's very useful. And not just for simulations, for observations as well. Yeah. So it's a very good tool if you can learn machine learning to have, especially it's become very trendy these days. And it's a good tool to have in your back pocket in terms of simulations when you're applying to a program or even a job. Having machine learning as a skill um, is really good.
Actually, madam, can you explain what are the main steps to build a physics simulation? Uh, People have guys actually below you choose any already build simulations or improve them for your works, or what would
Yeah.
be the
Okay. So there was some disruptions to the voice, so I'll try to answer your question to the best of my ability. So I think your question was if I'm using my own simulations, right? Or like using other simulations that are available.
uh, yes, madam. Other than that, can you explain some basic steps to build our own simulation in terms of physics based simulations?
Yeah, absolutely. Okay, so I'll answer. Okay, so the first question is whether I ran these simulations. For the n-body simulations, I didn't run these personally. This was run by my advisor for the Milky Way simulation and the n-body simulation. Now, that is to say, these are only dark matter only simulations, which I think took around like 2 weeks to run in a supercomputer. And the semiotic models work is what I did. So applying the stars and gas and feedback physics and different star formation physics from and reprocessing the n-body simulation is what I did mainly. So this process, let me show you. I didn't go in much into details into this, but happy to share. Okay. So right here. So you have the n-body simulation that have a series of snapshots in time that tells you how these dark matter halos evolve in time. And then you can just with the n-body simulation, you can't use that for Galacticus. You have to kind of process it to identify the boundaries of halos in the simulation. So you can use a halo finder to do this. And then once you identify the properties using halo finder, you can use a merger tree algorithm. This is basically connecting the snapshots or the halos across snapshots and building a history of halos across time and how they evolve. So once you have a merger history of dark matter halos, you can apply the semiotic model. So all of the things from halo finding to merger trees to semiotic models, I contributed, and the n-body simulation was run by my advisor. You can run the n-body simulation using, there are several softwares packages out there, and this was run with Gadget, where you can basically find run this type of simulation. I won't go into much details, but I'm happy to provide that information if you would like more. Another way we can build merger trees is by statistically building this with extended press sector merger trees. And these are much faster, so you don't need an n-body simulation. So some of the results that I showed you for Centaurus A, these EPS merger trees were run with Galacticus, and you don't need n-body simulations to run these. And you can get with Galacticus specific. Typically, these types of merger trees don't have positional information, but Galacticus can give the positional information based on a calculation it does. So this is very useful when building statistics. If you want to like look at larger number of galaxies, EPS merger trees is the way to go. For example, for like Roman predictions. So these trees, yes, these I can run. And specifically, if you don't have access to like a large cluster or a supercomputer, this building these extended projector merger trees allows you a way to simulate these galaxies very quickly in your own laptop. So that's another advantage. And one of the reasons I did this project using semiotic models is during COVID, I had a time where I didn't have much access to larger clusters. So this was the workaround for that. Did I answer all of your questions?
Yes, madam. Thank you.
Okay. So someone asked, I'm hoping to, I'm gonna repeat the question. I'm hoping to do a degree in astrochemistry, but I've always been really interested in astronomy. Do you know if there's any way I could get into an astronomy related career with this background? Absolutely. I think there's always astrochemistry. I haven't personally, but I think there are ways to get into astronomy with chemistry. So yes.
Thank you, everyone, for your questions. And I hope Dr. Sachi is always available to answer your questions and you can contact her. Um, and that's the wrap up for Q&A session. Once again, a heartfelt thank you to Dr. Sachi Weerasooriya for joining us today and sharing your expertise. We would also like to express our sincere gratitude to Professor Kalinga Bandar, the head of the Department of Physics, Dr. Rajita Mendis, the senior treasurer of the Astronomical Society, and Dr. V. Sivikumar and Dr. Prasanna Lienage for joining with us today, and everyone who worked behind the scenes to make this session a success. And of course, thank you to all the participants for being here with us this evening. We hope you enjoyed the session and we look forward to seeing you all in our future events. Once again, thank you everyone and have a great evening. Good night.